In this video, we'll look at conditional probability, multiplication rule, and the idea of independence between events. So conditional probability is motivated by the idea that sometimes we know whether something has happened, but some other thing remains random or unknown. Okay. So here's an example. In U.S. presidential elections, some states are reliably Republican or Democrat, but some states are so-called battleground states, and one of those that's been sort of contested in recent elections is Georgia. All right, and Georgia is sort of on the east coast of the U.S. Its polls close, before relatively early, let's say in the evening, and so you might learn which candidate won Georgia relatively early on, and in a close election, that could be very informative about a candidate's chance of winning the election. So, if the Democrat wins Georgia, maybe that would really increase the Democrat's chance of winning the whole election. But if the Democrat loses Georgia, it really decreases their chance of winning the election. Right? So in that case, you could think of the different events as like, the Democrat wins Georgia and the Democrat wins the whole election. Okay. So in general, let's let A and B here be two events, and you can see there's a ratio involved, so we'll just assume that the denominator is non-zero. That makes sense. That's the only interesting case anyway. And this is a definition of conditional probability. So I would read this as the probability of A given B, or the probability of A conditional on B. And let's put event B here as just circle the ring here of event B. Okay. So what is the conditional probability? It's the ratio of the intersection probability between A and B to just the probability of event B. Right? Why don't we go ahead and shade it in, and then maybe it'll make more sense. So A intersect B is the green area here, and B, that's just the whole blue ring there. So what we're saying with conditional probability is, let's assume, or maybe we're given information, that event B has happened. So we don't need to really be thinking about probability in terms of the whole sample space anymore. We can confine our focus to event B. It's almost like event B becomes our new sort of restricted sample space. We know, or we're assuming, event B has occurred. Okay, and within that, what share of event B is also occupied by event A? All right, that's what we're asking. So we're asking about the ratio of the green area to the blue area there, and that's why that's a reasonable definition of conditional probability. Okay. Obviously, you could switch these around and say probability of B given A, and again, it's the intersection probability, but it's divided by the probability of the conditioning event, in that case A. The multiplication rule it sort of barely deserves to be called a rule at all, because it's really just a rearrangement of the definition of conditional probability. All right, so what it says is, let's think about from the previous slide, probability of A given B. Well, the definition said that's probability of A intersect B over the probability of the conditioning event B. And if you just multiply through by probability of B to move it over there, you have one version of the multiplication rule. So it says the probability of A and B is the probability of B times the probability of A given B. Okay. Similarly, different version is if you started with the probability of B given A, then you know that's the intersection probability divided by the probability of the conditioning event, here A. If you multiplied that through by probability of A, then you would have this version of the multiplication rule. Right? Multiplication rule often applies when it's natural to think of the events as being sequenced in some way. So maybe, for example, you learn first whether event A has occurred, and then you learn later whether event B occurs. So maybe A is, just to continue our example, whether the Democrat wins Georgia, and B is whether the Democrat wins the election as a whole. Okay, so event A, there's some probability of that. and then there's maybe the probability of winning the whole election hinges very critically on event A. Okay, so if event A occurs, the probability of B given A might be quite high in that example, for instance. Okay, so that's the multiplication rule, but it's really just rearranging the pieces of the conditional probability definition. All right, just a little terminology note down here. These intersection probabilities are sometimes called joint probabilities. Okay. And the separate probabilities A and B are sometimes called marginal probabilities. So if you hear that terminology, that's what it's referring to. Okay, last thing for now is independence. So the definition of independence is events A and B are independent if and only if they satisfy this relationship. So this is saying that to find the probability that A and B occur, you could just sort of naively multiply the separate probabilities of A and B. Okay, that's the definition. Now, there's a consequence of this definition that falls out pretty quickly, which I think is a sort of more intuitive expression of the idea of independence. So let's think about probability of A given B, or conditional on B. So we know now, definition of conditional probability says it's this. Okay. Now, if the events are not independent, that's as far as you can go, okay? Because if the events are not independent, then you can't break that intersection probability into a product. But if the events are independent, then in fact that numerator is just the product of those two marginal or separate probabilities. And you can see what's going to happen here. The probability of B is going to cancel, and we're just left with the probability of A. Now, it's crucial to remember, you can only do that step right there. You can only cross this equal sign right here if A and B are independent, because we're leveraging that definition right there. But it gives what I think is an intuitive understanding of independence, because it says if A and B are independent, what we're saying is if you tell me event B has occurred, my probability of event A hasn't changed compared to if I had no idea that B has occurred. So the occurrence of event B has no bearing on the probability of event A. It doesn't influence the probability of event A in any way. Okay? And of course, this works symmetrically. So if you have two events, A and B, that are independent, then it would also have to be true that the probability of B given A is just the probability of B. So knowing whether event A has occurred doesn't influence the probability of event B. Okay. This is just saying what I've tried to say there. This is sort of the intuitive understanding. Independence means knowing whether one event has occurred doesn't affect the probability of the other. And then notice that if A and B are independent, then any A complement and B are independent, A and B complement are independent, A complement, B complement are independent. And that makes sense. So if I told you A and B were independent, it'd be really weird if, knowing that A had not occurred affected the probability of B. Like that can't be logically. And that's all that this is saying. Okay, so that's independence.